Welcome. In this video I'm going to show you how you can perform a post-hoc goodness-of-fit test using pairwise binary test and R. I'm using JupyterLab. I'm running R version 4.3 with only the basic packages pre-installed. Now I'm using JupyterLab, but the R code should also work just the same in, for example, RStudio. This is a test that is a pairwise test, so it will look at every possible pair of categories and check if which one might be significantly different from each other. It's going to be using binary tests, so a binomial most likely, but could also be a score or a wall test. Alternatively, you could only look at the expected counts for each category to see if those are significantly different from the observed counts. That would be a residual test. I have separate videos on all of those. Now, to show you an example, I need some general social survey data adjusted for example purposes. And once I've loaded in that data, I'll select one nominal field, the MAR1, which is the marital status, and to give you a quick impression, the table, which shows, for example, that 79 people indicated to be separated. In a separate video, I'll quickly show you how you can do it with my own library, which actually isn't too complicated. It simply has functions for all of this. And gives you then all the results. But if you don't want to use my library, there is, for example, the rstatics library. Once you've installed that, you can load it just as any other library. It gives me some warnings, but it seems to be doing still its work. It needs as input the observed counts, and I also set the adjusted method, which is the family-wise error rate, to Bonferroni, but you can change it to any you like. It shows all the possible pairs, then the sample size in the pair, and the estimate, which I think is the observed proportion from the first group. It shows the p-value and the adjusted one, so the family-wise error rate, in this case using Bonferroni, which is simply actually the number of pairwise tests that we've done multiplied with the p-value. Usually this is the column of interest, p-adjust. If this is below a predefined threshold of usually 0.05, we would speak of a significant result. Now, for example, this e minus 77 indicates that this 1.57 still needs to be divided by 10 to the power of 77, so this is extremely low. It would be 0. And then 77 zeros and then 157, so far below the 0.05 threshold. So these two categories are significantly different from each other in the population, most likely. Actually, all of them are, if you look, all the results are below 0.05. Unfortunately, though, it doesn't seem possible with this function to actually add your own expected counts. So let's have a look how we could do that. So again, I'll simply create one table. Oh, this doesn't need to be there. With the observed counts. Let's store the categories separately as a list. And let's also add our expected counts. Now, in this case, as you can see, they're not all the same. And I want to see all possible pairs, so I can actually use the comp end function for that. And that gives me now all possible pairs nicely as a data frame. Then I want to know how many of those I have, so the number of rows, which is 10. I need to adjust my expected counts for each of these pairs so that the ratios stay the same as with the original with all the categories. So I take the expected count divided by the total sample size of all the categories, not just the ones in the pair. That will be my expected proportion, and then I adjust that for each pair by simply dividing it over the sum of the two expected proportions in the pair. So that's what's being done actually in here. And then I added it to my little data frame. We can select only the data in each pair by simply running this little for loop, and that way each time we get the data just from the pair. With that data, we can then use a binomial test, a wall test, or a score test. I have separate documents on that, but just to show you how this could be done, here is that same beginning, and then I'll simply look at the sample size in the pair, the observed count of the first group, the expected proportion of the first group, and then I run the binom test function from R with that information, subtract the p-value from it, and multiply that p-value with the number of pairs that we have, so that's the number of tests that we've performed, so that's that Bonferroni correction. That could then go beyond 1, which is impossible for a proportion, so we take the minimum of 1 and that value, and then let's print all the results. And here we have the same results as earlier, or actually as you would see with my own library. Alright, I hope this was helpful, and thank you for watching.